Hello, I'm Robin Cole, and welcome to the Satellite Image Deep Learning Podcast. In this episode, I caught up with Marc Rußwurm to learn about meta-learning with Meteor. Our conversation starts with a discussion about meta-learning and the training of Meteor, and how this approach differs from the typical approaches taken to train foundational models. We cover the advantages and challenges of this technique, and discuss the fine-tuning of Meteor with minimal examples, as few as 5, for tasks like deforestation monitoring and change detection, and consider what the future could hold for this approach. Meteor showcases the significant potential of few-shot learning for processing remote sensing imagery and proves that it's possible to tackle tasks even when very few training examples are available. I hope you enjoy this episode. Hi, Marc. Welcome to the podcast.
Hi, thank you so much for having me.
It's my pleasure. Let's begin with where you work and what you do.
Thanks. I'm Marc Rußwurm. I'm assistant professor for machine learning and remote sensing at Wageningen University. And I have some background in geodesy, so from the earth science. And then I moved from computer vision into machine learning. And I'm now really in the intersection between both fields. And especially in Wageningen, we do a lot of applications. So how can we use modern machine learning methods effectively to bring them to do something good with them? That's the main topic here.
Absolutely. You recently worked on a piece of work called Meteor. I'm looking forward to hearing what that's about.
Yeah, that fits very well the recent work on a big machine learning models. So Meteor is about meta-learning, deep learning models for various tasks. So I think everybody is familiar with foundation models. So one model supposed to solve a lot of different tasks. Meta-learning is a way to formalize that in a mathematical way. So we are really optimizing a model on the objective to be good at various different problems at the same time, already in the training stage, where like the classic GPT type of pre-training models, they are trained on a different pre-training objective, and then we hope they are good on a set of downstream tasks, and they are very effective in that. But the idea is when we actually train them explicitly to multitask, then they also should be better on those individual tasks. And model agnostic meta-learning, that's the algorithm that we explored in that paper, is a way to formalize that with its own advantages and disadvantages, of course.
Fascinating. So foundational models are trained with some kind of pretext task, like fill in the missing pixels or something like that. In your case, meta-learning means you're training for specific tasks, I think classification, is it?
Yes, primarily land cover classification, but it's more like a contextual framework how we see data around the globe. Because when we look at land cover problems at different locations on the Earth, we can see each of that as a different task, as a different problem, and we see then the world as a data set of data sets. And there's some really fundamental advantages on this. So in classic land cover classification, we have situations where we have like ice and desert, two classes next to each other that the model needs to classify, but that doesn't not really make much sense because these classes don't really appear next to each other. So it's a much more realistic framework to think about a classification, a land cover classification problem in the Arctic as a problem including ice and tundra, and a problem in like the Sahara, including like shrublands and deserts. And classic supervised learning does not really capture this. So meta-learning is a way to formulate it as a data set of data set.
That's amazing.
That's the idea.
So it's not like with a GPT kind of model where you just train once on the massive data set. In this case, you're training once on smaller data sets or many times on many smaller data sets?
We split this one big data set of land cover problems around the Earth into many thousands of very small data sets. So we are going in this few-shot domain where we have global land cover data, and then we'll only look at data in the Sahara, and we take only 30, 40 images from the Sahara and train the model to distinguish different land cover classes there, and then optimize the initialization of this model. So where it kind of starts simultaneously to be good in the Sahara case, but also be good in the tundra case from the same starting point. So that's the core idea here.
Right. And is that supervised or is that unsupervised, that part?
It's supervised. We still need labels, but it's the learning algorithm that incorporates this hierarchical two levels of learning here.
Okay. So, and I gather there's some sort of novelty to the architecture as well.
So the model is smaller through to this algorithm, but it basically learns to compare. So you learn to compare few training images with the test images, and that also has a potential to learn very fine-grained patterns from those training images in different locations, rather than needing to learn all possible patterns of land cover across the entire globe in one large model. So that's an advantage here, that the models are smaller. And the disadvantage, of course, is that the dependence on the training data is much larger. So you need really high quality training data, optimally with hand-picked samples. So I think like human-in-the-loop learning would be a good application here.
Okay, so let's say I'm just starting totally from scratch and I want to do deforestation. Say, how much data do I collect? How much training is involved? How do I evaluate when I'm ready to fine tune?
So the good part here is the model is already pre-trained on those global land cover problems. So for a new problem in deforestation, you basically just need to annotate a few examples. So we have experiments on 5-shot learning, for instance, so 5 examples per class. In that case, it would be deforested and non-deforested. And the model would learn to distinguish these two classes with these few examples and then be able to predict. So that's one. It's explicitly trained on this few-shot learning objective. That's the point.
And it was pre-trained on a Sentinel data set, was it?
Yeah, Sentinel-1 and 2, the Sen1-2MS data set, basically. The main advantage is that it's globally distributed with land cover data with it.
And does this mean I can pick and choose if I use, Sentinel-1 or Sentinel-2, or I need to use both of them?
Yeah, we have some good experiments here as well, because there's this second fine-tuning phase where the model is able to adapt to the individual downstream task, and we can actually change the number of channels and only select the Sentinel-2 channels, or only the Sentinel-1 channels. And usually that wouldn't work particularly well because there's a lot of dependencies from the first layers to the next layers in the network. But in this case, because the entire smaller network is again trained with gradient descent and updated, it can adapt fairly well on even the first few layers. So that's a really nice thing here, that we are kind of flexible. We can also we train it on those multispectral images, but we can go to RGB 3-channel images by switching out the first layers, and it works relatively well.
Fascinating. And how was it to do the pre-training, in general?
How is it to train
is there lots of specialist hardware experience in the training process?
Like in any like in any big deep learning model. So it took about 2 days, 48 hours on a GPU, but on a single GPU. So we didn't scale up things too much. We took this Sen1-2MS data set, which is about 200 gigabytes in size and land cover data. We trained it for 2 days. Like the core thing is we need to build this data set structure. But that's basically how we got our pre-trained models that are then available on the GitHub repository, which is somewhat reasonable. But I think if you would scale it up a bit more with bigger compute, you would probably get a bit more benefit out of it. But that was not necessarily the core idea of this paper. The core idea of the paper was to show that this training algorithm works from land cover data, and then even though it's only trained on land cover problems globally, it can still be fine-tuned on very different other problems simultaneously. So that was kind of the main takeaway.
Mm-hmm. Fantastic. And what's some of the tasks that you fine-tuned on?
So that's the cool idea, that this can be actually quite different. So training tasks are land cover, and then at the downstream tasks, we have change detection on planet scope images, so fewer channels, higher resolution, and we provide 5 images per class of deforested images and 5 images per class for non-deforested images. And the model learns fairly well to classify then these 2 prototypes, class prototypes. Then we have urban density classification, so dense urban areas with sparse urban areas and so on, which is particularly difficult if you think about it, that it's only trained on land cover, which just has an urban class, and now it's really asked to distinguish different densities of urban areas. And we can even play with the definition of classes and really go into a more temporal change detection idea, because at the end, what we do in this fine-tuning tasks, we define a prototype of classes with those few training examples. And what we did is we looked at the the Beirut example, where this one warehouse exploded a few years ago, which left quite a big of a crater. And we took the first images in a time series and learned a class pre-event, and then took the last images in a time series and learned the event, the post-event class. So it's again a classification task in that sense. And then when we look at the whole time series and the probability for each of those, for both of these classes, we see that there is a sharp drop in the moment where the explosion happened. So it's more like, that was more like a conceptual idea that we can go away from this classic class definitions of class A and class B, and by defining few examples per class to really have something more dynamic of what a class is supposed to look like pre and post event.
Right. So in that sort of context, somebody that wanted to know when it happened, they would just have to find a before and after image and quickly train a model. I think you mentioned 5 examples, possibly even fewer examples for that. And then you would have an algorithm that could tell you, when this kind of significant change occurred.
It touches a bit this question of what is a task in the first place. In meta learning, we talk a lot about tasks, and we express tasks as a small data set, effectively. And what we do is we transfer our understanding of a problem to the machine learning model. And the way we transfer this understanding is through trained images. And classically in supervised learning, we need a lot of trained images to really train a deep learning model with many examples. But because a meta learning model is trained on explicitly on future tasks, we can just have a small set of images and then be fairly efficient on how we communicate these tasks that we have and that we would like to solve. And that's a bit different to like the classic foundation contrastive model methods, where we define these pretext tasks that we can easily sample at a large scale. But then we don't really know how well those pretext tasks align with our downstream target tasks. So in that sense, it's fairly complementary, but it serves a different purpose. It's explicitly trained on this few shot setting with few training images.
I guess the natural question is there a future where you can combine and get the benefits of the larger data set with the meta learning approach?
Yeah, it's a good question. Like, there's 2 challenges. One is the computational efficiency of this meta learning algorithm. So scaling it up would probably help a bit, because we still didn't perform too big of a training around this. But there's still limits on like how big you can do those models. So that would probably require changing this algorithm a bit to be more computationally efficient and be easier to scale up. But I think a key takeaway is more to be aware of this idea of tasks in the Earth observation domain, because we all think about data sets because that's what we have like in a grabbable, touchable way, but what is behind the data set, that those are just samples from a data distribution, and this data distribution is our task. And if we start to think about the Earth as an environment of different tasks, where we now need to build models to solve a variety of tasks simultaneously, then we can learn from this meta-learning framework to actually build new models specifically for those unique properties that we have in geographic data.
Absolutely. Really interesting stuff. So the code itself and the model is on GitHub. What do you want people to do with it?
I mean, there's basically 2 ways to use it. So one thing is we have the model weight, so everybody can download it and train it on their own downstream tasks. So that's more like the user perspective. That would be really nice to know what people do with it. The other side is to use the training algorithm and improve upon it. So include more training tasks, for example. So we have like all the training scripts in there as well, obviously. So one can basically take more training data from different problems, not only land cover classification problems, and just increase the variety of training tasks, and then use our evaluation scripts to measure how good it improves actually on those downstream tasks that we defined in the paper. Because that's how we limited ourselves a bit, because at some point you need to make a cut when you write a paper. But how far do you go? And we said, okay, let's stick with Sen12MS, which is like a fairly established data set only for like land cover and Sentinel-2, and show what we can do just from this set of training tasks. How many downstream tasks can we address? So I feel if somebody starts to train the same algorithm on like much more diverse training tasks, there should be quite a bit of a boost in performance.
Absolutely. Well, thank you very much for giving us the background on the project. It's been really fascinating to learn about meta learning. If people want to follow your updates, which is the best platform?
I mean, I'm on LinkedIn and Twitter mainly, but I think everybody can just find my email relatively easily and just write me an email. I answer usually the emails, so as much as I can.
All right, fantastic. I'll put that in the show notes. Well, been brilliant, Mark. Once again, thank you, and I'll talk to you in the future.
Yeah, thank you so much for having me. It's a pleasure.
Likewise. Bye.